Hi, today we will be reviewing motion graphs and how to use the information that they represent. Let's first start by drawing a velocity time graph, perhaps of this car's velocity. We will of course graph time on the x-axis and velocity on the y-axis. And now we have a wonderful graph and we can begin pulling out some of the useful information. Let's say that we need to find the displacement of the car in the first half of its journey. Well, to begin with, let's first assume that the velocity was constant, just to simplify the problem a bit. We know that velocity is a change in displacement over time. So, by rearranging that equation to solve for displacement, we find that it is a simple multiplication of velocity and time. Graphically, we see that this multiplication is essentially finding the area enclosed by the function and the x-axis. Now with this in mind, let's return to the actual function and try apply the same skill. Fortunately, the IB does allow for approximations, so there are some methods we can use to approximate the area. Firstly, we can draw a series of rectangles spanning from the x-axis up to the function. If we calculate the area of each one and add them up, we will get the approximate area enclosed by the function. Now, alternatively, if there are grid lines on the graph, we could calculate the area of one box and then multiply by the number of boxes below the function. Let's suppose that we need to find the average acceleration of the car in the first half of the trip. And again, we will straighten up some of the curves to make it a little bit easier. Let's look at the definition of acceleration. Acceleration is the change in velocity over the change in time. And on a velocity time graph, what we see is that acceleration corresponds to the slope of the function. With this in mind, let's return to the original function. We can find the average acceleration by creating a line segment between 2 points on the function and calculating that slope. However, in some cases, we may be asked to find the instantaneous acceleration. And again, we could do this with calculus, but it is not necessary. To do so without it, we can draw a line that is tangent to some point. Next, we calculate the slope of that tangent line. The slope of that tangent line will be the instantaneous slope of the point at which it is tangent to. The tools and methods we've just developed for velocity time graphs can be applied to other motion graphs like displacement time graphs and acceleration time graphs. So let's first consider the displacement graph of our car's trip. Let's suppose we calculate the slope of the function. In doing so, we actually find the velocity of the object. The definition of velocity is displacement over time, and this is equivalent to the slope of a displacement time graph. Now, like before, we can calculate the average velocity or instantaneous velocity depending on how we draw the line. Now let's suppose we calculate the area underneath the graph. The area under the graph would be calculated by some variation of the equation A is equal to displacement times time. Interestingly enough, this value does not actually represent anything useful which we can use. So when it comes to displacement time graphs, there's no need to calculate the area under it. Finally, let's have a look at acceleration time graphs. Now I have graphed the acceleration of our car onto the graph, just so we have some consistency. Unlike the displacement graph, the area enclosed by the function and the x-axis does provide some useful information. Given that acceleration is defined as velocity over time, if we were to rearrange the equation such that acceleration is being multiplied by time, we find that the area enclosed by this curve is the change in velocity. Now let's say we calculate the slope of the curve, and it does give some insight into the object's motion by providing us with a quantity which is known as jerk. Jerk is simply the rate at which the acceleration changes. However, this is most likely not going to be useful for our purposes and thus can be ignored. Throughout the video, I've only been using sine and cosine functions. However, the two tools I've quickly gone over can work in any situation, regardless of what type of function is being graphed. To wrap things up, let's quickly do a recap of what we just covered. Let's start with displacement time graphs. Calculating the slope gives us the change in velocity, and the area is not very useful. When it comes to velocity time graphs, calculating the slope finds the change in acceleration, and calculating the area finds the change in displacement. Lastly, acceleration time graphs. The slope is not useful in our cases, however, it does provide a quantity, and the area is the change in velocity. Thank you for watching the video, guys. I hope you enjoyed and maybe got something out of it. I don't know. Also, if you have any suggestions on what we should do differently or suggestions on future topics we should cover, feel free to email that to us, or you can just put that in the comment section as well. Once again, thank you very much for watching and have a lovely day.